So, okay, uh, in our last class, we talked about minimum spanning tree. Before that, we have already discussed about Eulerian circuits, Eulerian graphs, and Eulerian paths, and then Hamiltonian circuits. And then at the end, we already talked about traveling salesman problem. And then in our last class, we talked about minimum spanning tree, and we have already seen how to find a minimum spanning tree for a connected graph using Prim's algorithm as well as Kruskal's algorithm. In today's class, we are actually going to do another very important aspects of graph theory, and that is known as planar graph. So in my first class, when I started the graph theory as an application, I talked about an example, the utility problem example. Like for example, suppose there are three houses and say three services are there. For example, say electricity line, maybe the cable line, and maybe the water line. Okay, so they are the three utilities. For example, say this is say telephone line, say this is water line, and say this is cable line. And so all of them, there must be some connection with this home. So this is home 1, home 2, and home 3. So all each of this home should have the connection from these three utilities. For example, it should have a telephone line, it should also have a water line, and it should also have a cable line. Similarly, say this home should also have this and this connection, and for example, for the last one, it should also have this, and so on. So the question is, can you draw this graph in such a way that one line should not cross others? So there must be another line from here. Yeah. So the question is, can you be able to draw this three services or three connections should be gone to this each of these houses so that no edge will intersect others. For example, sir, in this case, we have seen that this is a crossing point. This could be a crossing point. This could be a crossing point. For example, for maintenance, if say this water supplier, they want to have some kind of maintenance, so they will dig up the soil and they will try to make it fixed. While doing so, if there might be a crossing here, and it may happen that while you are doing some maintenance work for water pipe, it may happen that the telephone line or even the cable line may get damaged. So it's a better idea to install all these lines in such a way that they should not intersect each other. For example, suppose I have already mentioned about this example. Suppose this is my graph. This is my complete graph with 4 vertices. We call it K4. And here we can see that there is a crossing here. So the question is, can we redraw the same graph keeping all the properties intact? Is it really possible to redraw the graph so that there should not be any kind of crossing? The answer is yes. Of course, we can draw this. Okay, so we can draw this by using. Okay, so we can draw this like this. So this is there, and for this, instead of going through this, we can have this. So you can see that none of these edges will cross each other. So this kind of drawing is very important. For example, while we are going for metro stations. So in Kolkata, usually we do not have any metro line. We have only, at present, only one metro line is working, but it may happen that there are many metro lines. In abroad, you might have seen that similar kind of situations where many metro lines are crossing each other, and they might be of different companies. So you can understand that if you have a crossing, then it would be difficult, because if you have two trains are coming in the, I mean, almost at the same time, one has to wait, otherwise there would be a collision. So while then making the metro lines, or while we are preparing for this metro lines, it should be better to install the lines in a different level. For example, suppose this is the ground level. So one metro line is going through this level, or another metro line should go through another level. So that the crossing may be avoided. And that is one of the important, interesting applications of graph theory. Not only that, when we see you can see that your mobiles, day by day, the size of your mobile or the size of the televisions, everything is gradually going down. So the size of the mobiles or the size of the televisions, actually they are synced now. That means the hardware are becoming in you are I mean the people are installing the hardwares in such a way that within a small space they can install everything. Now, when one electric wire is going like this, and if you have a crossing over it, then there might be a problem here, because it may increase the heat, or if something happened here, then it may affect at this point. So it's better to fabricate your this chip in such a way that they should have minimum number of crossings, and there the planar graph comes into play, and that's why for a practical purpose this planar graph plays an important role. So as I just now mentioned, you can see that this is a small chip, and all the fabrications are done in such a way that one wire should not overlap with others, and it should be a minimum way. So here you can see that the subway system can also be done in that way. Utility I have just already mentioned. And in the circuit board, there are plenty of such applications of this planar graph. Now, can anybody be able to draw this? So you can see that there are many places where you have the crossing. So here one crossing is there. Can anybody draw this image keeping all the things intact, but it should be written, or it should be drawn without having any overlap of edges? That means without crossing any of the edges. Can somebody be able to describe how to draw this? So it looks like a three-dimensional cube. Okay, any
So,
idea?
so we
Yes,
can draw two concentric squares and join the vertices.
very good. So like this. So you can see that here there is the same thing can be done. It can be thought of like a projection of this inside this, right? So you can very well thought of, so this part is actually projected inside this, but the size should be the less, so that it will go there, and then connecting all the, so all the properties, graph theoretic properties that this image has exactly the same properties this image has. So though it looks like they have some crossing overlapping here, but here you can draw in such a way that there cannot be any such overlapping. Now the question is, can every graph be drawn in that way? So that's the basic idea of planar graphs. So what could be the condition that to check whether a graph is planar or not, or is there any easy method to do so? Okay, so it's a complete graph K5, and let us try to check whether this complete graph is planar or not. Can anybody, could you please try on your own to check whether you can draw this K5 on a without having any kind of overlapping of edges? So this is my graph. Okay, so let's try with, I need to have this complete graph. So suppose I draw this, okay, till now there is no problem. I draw this, till now there is no problem. I cannot draw like this. So maybe I can join this one. So till now there is no such problem. So 1, 2, 3, 4. So here all the four edges are already exhausted. So I don't need to think about much on this vertex. Now for this vertex, I have 1, 2, 3, 4. So that is also exhausted. So I have all the four edges from this vertex. Now how many edges that you need to put it here? So here 1, 2, 3, 4, and then one more vertex, one more edge it should have. So I can draw like this. Okay. So here also I have 4 edges. So degree of this is 4, degree of this is 4, 4, degree of this is also 4. Now I am left with this uh, 2 vertices. Now I need to join them, right? Now how do I join them? So that there should not be any overlapping. Just kind of a small observation that this point and this point, they are basically lying in a kind of region which is closed. For example, this point either lies within, you can think in a different way. So you may think that this lies within this region, this point, okay? And this is outside, this point is outside that region, bounded region. So to join it, either you have to exhaust through this, and then this, or you may have to come through this. But if you want to come through this, then you certainly uh, have to cross this edge. So intuitively, you can understand that, okay, for K5, it's not, sorry, K5, it's really not planar because you are unable to draw. So try to draw yourself to convince this in any way. If you want to draw, then you will find that there must be some kind of crossing. Okay. So K5, as I mentioned, you won't be able to draw without having any crossing of the edges. Okay. Again, this is K33. So it's a bipartite graph with parameters 3 and 3. So if you also have a look at this, and if you also try to draw this image, then also you'll find that you cannot draw like without crossing this edges. So that means K33 is also not planar. So there are formal proofs to do so. So I'm just giving you the intuitive idea, and the proofs are not within the scope of our syllabus, but the proofs are not that difficult. It follows from some theorem. I will going to give you the theorem, proof of this theorem, but you can of course check how to prove whether K5 or K33 are non-planar. The proof is not that difficult. Okay. But the interesting idea here is given by Euler, and you can understand that it's a very well-known result for planar graphs. And it says that for a connected planar graph, this relation happens. So what is that relation? V is the total number of vertices, edge is the total number of edges, and F is the total number of faces, or some books it says that it's regions. So what does it mean? For example, suppose I have this graph. So here the number of vertices are basically 1, 2, 3, and 4. That's why V is 4. Edge set, how many edges are there? 1, 2, 3, 4, 5, 6. So there are 6 edges are there. Now the question is, what do you mean by region? So firstly, have a look at this. This is a kind of closed graph, right? So it has 2 regions. So it's bounded by 3 edges. So it's a region 1. Again, this is another region. This is another region. And outside, that means the complement of whole this, that is an unbounded region. So they are bounded region, and this R4 is the unbounded region or face. So we call them as a region. That's why I have 1, 2, 3, and 4 regions based on this. So here I have this face, or number of faces, or the number of regions are 4. So you can see that it satisfies V minus E plus F equal to 2. That means 4 minus 6 equal to minus 2 plus F is 4. That means plus 2 equal to 2, and it satisfies. And that's the celebrated theorem known as Euler's planar graph theorems. Okay, so let us try to have this maybe, so some graph. Let us try to get some idea of it. and say maybe like this. Okay. Now somebody tell me how many vertices are there. So V1, V2, V3, V4, V5, V6. Okay. And how many edges are there? So this is E1, say this is E2, E3, E4, E5, E6, E7, E8. I think there are 8 edges, right? Okay, all the edges are exhausted. Now tell me how many regions are there. So you can see that many regions are bounded and one unbounded region is there. So I call it the unbounded region as R1. Then this is R2, R3, R4. So there are four such regions, among which this one is the unbounded region, and this is they are all bounded regions. Now let us try to check. So what is V? So the number of vertices here is, so V is how many vertices? Six vertices are there. E is number of edges. How many edges are there? E7. E7, E8. E8 is there, and the number of region or face equal to 4. So you can see that, sorry, not E8, it should be 8. Okay. So 6 minus E is 8 plus 4 equal to, so how much? It's 2. And that is satisfied. And that was, this result was given by Euler. And it's a nice result. It gives a connection between the number of vertices, number of edges, and the number of regions or faces of a connected planar graph. Let us try to have a proof of this. Okay, we just give a intuitive idea of this proof. Okay, the proof will be given on by principle of mathematical induction on the number of edges in the graph. Okay, it will be given on the number of edges of the graph. If e equal to 0, as I have already mentioned, it's for connected graph. If e equal to 0, what does it mean? What does it mean? If I have a connected graph with number of edges equal to 0, then how the graph should look like? A
Single vertex.
connected graph. Yes. So a connected graph with e equal to 0. That means there exists no edge, but that's a connected graph. So it should look like a only one vertex. Okay. So here v equal to 1, e equal to how much? E equal to 0. And what would be the region? How many regions are there? So only the unbounded region. So f equal to number of faces, f equal to also 1. So what is the result? B minus E plus f should be 2. Let's suppose look at this. This is 1 minus 0 plus 1 equal to 2. So the result is true for the initial conditions. Okay, which is clearly right. Okay. Now assume that, suppose the formula works for all graphs with no more than n edges. That means we assume that the result is true for this particular result is true for all graphs with n vertices. All, I mean, connected planar graphs with n vertices. And let G be a graph with n plus 1 such edges. So not vertices, this is n edges. So we are doing the induction on the number of edges. So we assume that the graph G, we consider a graph G with n plus 1 edges. So mind that G is a graph, I mean, the result is true for all graphs with n edges, and I am considering now the graph with n plus 1 edges. As I mentioned, G, okay, G cannot contain a cycle. So two cases may happen. Either G contains some cycle or G may not have any cycle. If G cannot have a cycle, then what should be the structure of this graph? So G is a connected graph. G has no cycle. In our last class, we have already seen that this has to be a tree. So the definition of tree is like that. It's a connected graph without having any cycle. So case one is G does not have uh, any cycle, and then it must be a tree. Okay, in case of tree, what happens in case of tree? If you have a tree, for example, suppose this is a tree, suppose this is a tree. So if I write like this, so see, if every vertex does have two of these edges, so this kind of graphs are known as binary graphs. Okay, so everywhere you have two bifurcations, either this way or this way. And usually in graph theoretic sense, I call this as a root. So we call this graph as a rooted tree. Rooted tree. Okay. So if your graph is like any tree, then what will happen? The regions is how many regions or f is there? F is basically the unbounded region. That means f is 1. If number of vertices is n, then in our last class we have already seen what would be the value of e. If you have a vertex n vertices in a graph which is a tree, then how many edges will be there? Can anybody tell me? If n is the, for example, suppose how many vertices are there? One, two, three, four, five, six, 7. Now tell me how many edges are there? So one, two, three, four, five, 6. Now tell me, if n is the number of vertices, how many edges will be there in a tree? Last class we have already discussed about it. It should be n minus 1, right? So if you have v minus e plus f equal to n plus, sorry, n minus n plus 1 plus 1 equal to 2. So if this is a tree with n vertices, then we understand that the number of faces will be 1, because only the unbounded regions are there, no bounded regions are there within this. In that case, f is 1, and if it is a tree with n vertices, then the number of edges must be n minus 1, and in that case also the this principle of inductions hypothesis, that is also satisfied. So basically, if it does not have any uh, tree, then, sorry, any cycle, then we are basically done. So the second case, G contains at least one cycle. So G might have more than one cycle, but it should be, G should have at least one cycle. So sorry, take any edge P that's that is on the cycle. So now we are considering the case 2. That means you have a graph G and it has some cycle. So suppose it has some cycle within it. The graph may look like this. Anything, it might have more than one cycle, like this. Anything may happen. So suppose it has some at least one cycle, and say I think P is the and region, okay, and P, peak NHP that is on that cycle. Take any, for example, suppose this is my P. Okay, P is any edge on that cycle. Consider this to be a edge. Okay, since the cycle separates the plane into two regions, so whenever you will have cycles, that means that will be some bounded region. So a cycle will always separate region 1 and region 2. There might be more regions. For example, here there are many more regions are there, but still if you have a cycle, since the cycle separates the plane into two regions, if you have a cycle, then it will separate the planes into two regions. For example, if you have this as a cycle and this as a cycle, then it will separate the whole thing into two regions. Okay. So since a cycle separate the plane into two regions, the regions to either side of P must be distinct. That means this region and this region must be distinct. Okay. For example, if this is the case, then you have many such regions. So this is say R2, this is R1, this is R3, R4, and so on. So a cycle actually separates, and these all regions are different. But when you remove the edge P, we merge these two regions. For example, if you remove this P, then you are basically merging these two regions. For example, if you remove here this two, this edge, for example, if this is your P, then basically it becomes like this. It becomes like this, only this. So you don't like this. So you don't have any R1 and R2, two distinct regions. Two regions become the same, R1 equal to R2. So all the regions in this case will be unbounded region. But here, if you remove this P, then what will happen? This region, so R2 and R3 become the same. But if you remove this edge, then R2 and R1 will become the same. So that this region becomes unbounded. So that will merge with R1. So that's what it says. When we remove the edge P, we merge these two regions. So G dash has one fewer regions than G. So we started with a graph G that has say some regions, say F many regions. If you remove one point P, one edge P, then it will suddenly have F minus one many regions. Since G dash has n edges, so the number of edges uh, for G dash, so in G dash you started with you started with n plus 1 edges. Then you remove one edge from G to get G dash. So now G dash has n edges. So G has n plus 1 edges. So G dash will have n edges. Since G dash had n edges, the formula works for G dash by the induction hypothesis, because we are actually using the induction hypothesis on the number of edges. So in our assumption, we assume that the result was true for no more than n edges. So as a result, the result is true for G dash. So in case of G dash, this result will be true, like V dash minus E dash plus F dash must be equal to true. But if you just remove one edge, but no vertices has been removed. For example, here we have just removed this point, this edge, but this vertex and this vertex were intact. So as a result, V dash should be equal to V. E dash have reduced one more vertex, one more edge from G, and F dash is already one more less. So substituting these values, you will get that is also equal to 2. That is V minus E plus F equal to 2. Is that is the result of proof clear to all of you? It's a very easy idea. But based on this Euler's result, this V minus E plus F equal to 2, few corollaries are there. And based on this corollary, someone may be able to prove very easily that this K5 as well as this bipartite graph K33 are non-planar. So you can check on your own by using some internet, or you can try to prove it by proving some corollary, and that will be done. Okay. Now I am going to show you another interesting result that was actually done by Kuratowski's theorem. So these graphs, this K33 and K5 are known as Kuratowski graphs. So what it says, to understand that theorem, let us first try to understand what do you mean by elementary subdivision. So operation in which a graph are obtained by removing an edge and adding the vertex W and the edges is known as elementary subdivision. What does it mean? Let me try to explain. Suppose I have this, suppose I have this graph. Okay. Now what I'm going to do, I first remove this edge. Okay. So then it will look like, the graph will look like this. Okay. Then what I'm going to do, I am going to insert another vertex here, new vertex right here, and I just draw, add them. So what I'm doing, I just adding one extra vertex to give a kind of partition of this. Okay. So it's basically again subdivided it. So I subdivide it. So it's actually subdivided. So it may happen that again then you may remove this edge and you may insert one more vertex and you can add this. So again this is a called subdivision. Okay. So what again, if you look at this operation in which a graph are obtained by removing an edge. So you are first removing this edge and adding a vertex W in between and the edge UW and WV. So this operation is known as elementary subdivision operation. Now, what do you mean by homeomorphic graphs? So in topology, you might have heard about this term homeomorphic. In graph also, similar, not similar, I mean, in a graph theoretic sense, it's different. It says that graphs G1 and G2 are termed as homeomorphic if they are obtained by sequence of elementary subdivisions. Okay. For example, this graph, so initially I started with this, then I had one elementary operation to get this one. So initially it had this, then I had this, and after that I used subdivision operation here to get this graph. So you can understand that two extra vertices have been introduced here. Still we have the same property or same graph that was initially there. So initially it was not there. So initially the graph looks like this, and this graph are homeomorphic because in the first step we have removed this edge, we had this, and then after that we have removed this edge to get this. So if we have, so what it says, G1 and G2 are termed as homeomorphic if they are obtained by sequence of elementary subdivisions. Okay. So that's these two basic definition, and based on that, the Kuratowski's theorem is there. It says that a finite graph is planar. It's very important. A finite graph is planar if and only if it does not contain a subgraph that is a subdivision of the complete graph K5 or the complete bipartite graph K33. What does it say? It says that a graph G is planar if and only if it does not contain, that's very important, if it does not contain these two subgraphs, either K5 or K33 or any subdivision of that. For example, suppose I have initially this graph. Okay. So it looks almost like, it looks like say 1, 2, 3, 4, 5. It looks like K5. But you can understand that this is not exactly K5, but this is a kind of homeomorphic things of homeomorphic graph of K5. Because here, if you have this, you can just remove this, then this point will be removed and this edge will be there. Or then you can have this one, because you have already explored many times the elementary division property. So you can join this one, then join this one, and join this one. Then ultimately you will get K5. What it says, it either does not contain K5 or K33 in the subdivision form. Then we call it then we can very easily check whether a graph is planar or not. For example, this graph, so it is not really K33, but you can see that this is a subdivision of K33, because with this two edge, if you remove this vertex B, then suddenly this will join with F, and that is nothing but K33. So this graph really does not contain K33 directly, but it has a subdivision of K33. That's why this graph is also not planar. For example, if you have a look at this, so this is known as Peterson graph. Just have a look at this animation. So what I am doing, I am basically merging the elements, and ultimately it will look like K33. So again, if you look at this, you start with K. This is known as Peterson graph. Just have a look at the vertex which I am merging, and then we are collapsing things to get K5, K33. That means Peterson graph is also non-planar because it contains a subdivision of K55 as a subgraph inside, which is lying inside this Peterson graph. So this is a important graph in graph theory. So this is a three regular graph. That means the degree of each vertex, you can see the degree of this vertex. Okay, so this is a Peterson graph. So this is not a regular graph in that way. So degree of this vertex and this vertex, what is the degree of this vertex? This vertex degree is 2. But it's very important graph because it has lots of property in graph theory. So this is known as Peterson graph. So you can understand now this Peterson graph contains K33 as a subgraph which is embedded inside this. It really does not contain K33 directly, but by merging something, you can ultimately come up with this vertices. So Peterson graph is not a planar graph. Okay. Now I will again come to another interesting property of graph theory, that is known as vertex coloring problem. What does it mean? So coloring, we all know. Suppose we have this graph and I want to color the vertices. Now you can see that here I have given all the vertices are there. One, two, three, four, five vertices are there, and all these five vertices So you can always color a graph with the number of vertices will be same as the number of distinct colors. But in graph theory, that is not that interesting. The definition of coloring means a graph, a coloring of a graph is an assignment of colors to the vertices of the graph so that no two adjacent vertices have the same color. So see here, all the vertices are having different colors. As a result, no two adjacent vertices will have the same color. But see, here I have colored it with only three colors: green, red, and blue. See, if I consider this, then two adjacent vertices will be of different color. If I have this, then also we have three colors. Here I colored it with five different colors, but here I colored it with only three different colors, namely green, red, and blue. So now you understand what do you mean by a coloring. Now tell me, can you give me the coloring of, say, maybe, okay, maybe this graph, how many colors? So you can very well give four different colors, but can you try to make it a minimum number of different colors so that it could be colored with, say, one, two, three, four, the four vertices with minimum number of colors so that this property is satisfied. Suppose I give this color to be a black color. Now by the property of coloring, if it has to be a proper coloring, if I consider I cannot put it black, I cannot give him black, and I also cannot give black, because otherwise two adjacent vertices will be of the same color. So I need to find some other color to give it. Say for example, suppose I give yellow here. So I put yellow here. Okay. So I cannot put yellow here. I cannot give black as well as yellow here. So say I give, say, blue. So this color is blue. So I actually require three different colors. Now, what could be this color? I can give any other color than this, but I want to minimize the number of different colors. So what should be this color? What color should we give here? Anybody? To minimize the number of colors?
Yellow. Yellow.
Yellow. Perfect. So if I give yellow color here, then there will be no conflict, because this, if I consider this edge, then I have two different colors here and there. If I consider this edge, I have two different. If I consider this, different, different, and different. So that means we can color this graph with at least three different colors. Okay. So this minimum number is having a special name, and that has lot of applications in real life. Okay. For example, if the vertices of a graph represent academic classes, so that means suppose UG1, suppose in this class, say this is a special paper class. So somebody might have taken the linear programming and optimization techniques. So you can understand that these two classes are disjoint, because nobody should take the both the subjects, because that is optional paper. So our graph theory, number theory, and combinatorics is one paper. Another optional paper is optimization technique and linear programming. So a student cannot take both the classes in a course. So what you understand, that you can very well run the classes in a same time. So in the routine, usually we put the both the classes at the same time. That means there won't be any conflict. But if it happens that some students are common there, then you cannot run the both classes simultaneously, because a person cannot be present in both the classes simultaneously. So here also this coloring problem plays an important role. So it says that if the vertices of a graph represent academic classes and two vertices are adjacent, if the corresponding classes have some student in common. That means if you have some common student, then we call these two vertices are connected. Then a coloring of the vertices can be used to schedule class meetings. Okay, is it clear to all of you? Okay. Another thing is that if the vertices of a graph represent radio stations. So for example, you nowadays you all listen to FM. So if you have FM, then you must know that there must be some frequencies, say 92.6, maybe 98.3, and so on. So they are all frequencies. Now, if the frequencies are like this, for example, one radio station, FM station, their frequency is 98.3, and another frequency maybe say 98.4, and maybe another radio station is 98.2, then you will understand that if these frequencies are very close or nearby, then it will be very difficult to adjust them. That means if you are just going for 98.4, then suddenly it may go either to 98.3 or 98.2. If they are three distinct FM radio stations, then it would be very difficult for you to adjust the radio station. That's why the frequencies should be little far off. Here also, this assignment problem, the graph coloring is playing an important role. Again, If the vertices of a graph represent traffic signal at any, say, crossing, and two vertices are adjacent, if the corresponding signals cannot be green at the same time. So two vertices are adjacent, that means they will have the same edge, or they will be connected through an edge if the corresponding signals cannot be green at the same time. A coloring can be used to designate sets of signals that can be green at the same time. Now you can use the coloring problem to solve this kind of scenarios. So there are plenty of such examples where you can use the graph coloring. So now I'll just giving you another important term that is known as chromatic number. So in graph coloring, as you have seen that to color this, you can color by, so there are five different so Anubhav, could you please turn off your Anubhav, could you please turn off your mic?
Sir, my mic is turned off.
Okay, now it's turned off. Yeah, thank you. Some noise was coming. Okay. So if you consider this graph, then you can understand there are five vertices. So you can color with five colors, but I want the minimum number of colors to be used here. So here you can see that you can color it with three colors. Can you be done it with less number of colors? Can you do it by two colors? Can you be able to do it by two colors? No, because already a triangle is there. To accommodate triangle, you have to have three different colors. So you cannot do it by two colors, because if you are going to do it by two colors, then at least one of them will be adjacent, and you cannot do it by two colors. So it has to be three, and with this three, you can also use that three colors to color these 2 points. So the least number of colors needed to color the graph is known as chromatic number. Okay, and there is a term called k chromatic number. A graph that can be assigned a proper k coloring is k colorable, and it is k chromatic if its chromatic number is exactly k. So it's a three chromatic number. Okay. Okay. So let us try to have this. Suppose I have a cycle. So in case of a cycle, suppose I have a cycle, say, now how many colors do you think that should be required to color this? How many colors?
Two,
Just
sir.
now two. So you can do it by, say, this is by black, say this is by red, say this is by black, this is by red, again this is by black. But if I have, say, five length cycles, then how many colors? Suppose I start with red, then black, then say red again with black, and then you will be left with one vertex. And then you cannot give it red, because if it is red, then they will be adjacent. So you need some extra color. So it depends whether the length of the cycle is even or odd. If it is even, so this is 1, 2, 3, 4. If it's an even length cycle, then two colors are sufficient. But if it's an odd length cycle, then three colors must be there. Okay. So let us have a look at this. So this is a complete graph, right? So for a complete graph, how many colors should be there? So suppose you have a complete graph. So how many colors should be there? Say this is K4. How many colors should be there for a complete graph?
Sir, the
Four.
n.
Yes. So for a complete graph Kn, you can understand that all the vertices are adjacent to any vertex. So all the vertices should be given different colors. So you cannot color with the same color, right? So all the colors should be different. And say this is black. So all the colors must be different. So for Kn, the chromatic number should be n. For complete bipartite graph, how many? Say for example, I have three. Okay. For that, how many?
So two.
Two. Because these are not connected. So you can put maybe black and you can put red to the others. So for KNM, it would be 2. Okay. Suppose this is a graph. Okay. Can tell me what would be the chromatic number for that? Okay. Can able to tell me? Yeah. So this is the color basically. So you can see that I have colored it with 4. It's not very easy to color it with 4. So you have to think a bit. It's not that difficult, but it's not very trivial to color it with 4. So you can understand that it contains a complete graph with 4 vertices. So this is a complete graph with 4 vertices. So to color this, you would need at least 4 colors. So if you have a complete graph embedded with that graph, then you will at least require n many distinct colors. So that's why you have at least 4 colors you require. And with these 4 colors, you can color this. Okay, you can take a screenshot of this image and then you can try to color with these 4 colors. Okay, very interesting problem and theorem, and the proof is out of our scope. It says that it's a 4 color theorem. It says that the chromatic number of a planar graph is no more than 4. So this one was a planar graph. So you will suddenly be able to color this with 4 colors or even less colors, but the number of colors will be required to color this planar graph or any planar graph cannot be more than 4. So that's known as celebrated 4 colors theorem. And many things you can just Google it and you will able to understand or you will able to learn many things for this particular theorem. Okay. So I am going to give the last part of the graph theory, that is independent set. So what is the meaning of independent set? Suppose you have a graph. So this is a graph and you can see that. So this is the vertex set. So here the vertex set has 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices are there. So independent set will certainly be a subset of a vertex set in such a way that the set, there is no edge between these vertices in S. So S is a subset of the vertex set, and you will find that there should not be any edge among these vertices. For example, if I consider my S to be this red colored subset, so this is these 3 red color sub elements or vertices, if I consider to be within S, then you see that there exists no edge between these 3 points or 3 vertices, right? So this set is called an independent set. For example, here, if I consider this, the red colors, they represent an independent set. For example, here, these 3 red colors also represent independent set, or here, this 4 or 5 red colors also independent set. So the question is, what could be the maximum independent set? So a maximum independent set is an independent set of largest possible size of a given graph. The size is called the independence number, this size. So the maximum independent set size, the size of the size means the number of vertices within that independent set is called the size, and this size is called, this size of the maximum independent set is called the independence number. Can you very quickly find the independence number of this graph? Anybody be able to tell me what would be the independence number of this graph? This particular graph, what would be the independence number? Anybody? What could be the independence number of this set? Pratik, any?
So the concept is not clear yet.
Okay, so independent set means, see, if I consider this red colored mark, so there are three vertices. So for example, if I consider like this, if I draw like this, suppose I have 7 vertices, 1, 2, 3, 4, 5, 6, this, and this. So suppose this is my graph. Okay, and say I just write them down. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So if I consider this vertex, not maybe not this, yeah, this vertex and this vertex. Do you have any edge between these two? So if I have s equal to 1 and 3, do you have any edge between 1 and 3?
No, sir.
If I have my s to be 1, 3, and 5, do you have any edge between any pair of these two vertices? These three vertices? Any pair of these three vertices? So 1, 3 is not an edge, 3, 5 is not an edge, and then 5, 1 is also not an edge. Now can you, so this is, say this is my S1 and this is my S2. So S1 is a subset of S2. Can you be able to find another S3 which is strictly bigger than S1 or S2 such that S3 has this property that take any pair of all pair of vertices, you will not be able to find any edges among all these vertices. Can you be able to find any such extra point which is strictly greater than S3, S2? Any vertex?
No, no, sir. No such sets are there.
So this is the maximal independent set. Okay, and the maximal cardinality, the maximum cardinality is 3 here. You could have also taken this one, say maybe this vertex, this vertex, this vertex. That means you can consider maybe S2 dash equal to say 2, 4, 7. But again, you cannot take any extra vertex here having this property. That means there will not be any edge among these vertices. You can understand that you cannot take 8 anywhere because If you take anywhere, there will be a vertex from there to any other edge, any other vertex. So you can see that 3 is the maximum cardinality of all the independent sets. So consider all the independent sets and consider the cardinality of each of these independent sets. Takes the maximum, that would be the independent number. Now it's clear. Now tell me, what is the independence number of this set? What is the independence number of this set? Independence number
Sir,
of this.
3.
This is 3. Why? Okay, let us draw this. How many it was? 3 by 3. Okay, 3, 3. Right? So this is 1, 2, 3, 4, 5, 6. Now tell me, what is your S1? Somebody? There should not be any vertex.
Sir, 1, 2.
1, 2. S2.
1, 2, 3.
So there is nothing called S1, S2. So you can understand that S2, S2 here, 1, 2, 3, you cannot have more than 1, 2, 3, right? I mean, you cannot have any vertex, any subset S3 which is strictly bigger than 1, 2, 3 having this property. Similarly, S2 dash could also be 4, 5, 6, right? So here the independence number is 3. Similarly, you just try to find the independence number of these images. Just please take a screenshot of this and then you will able to solve this. So this is the 9 blue vertices. So they are the independent set. This is the maximum independence set. So 9. So here this is called generalized Peterson graph. And this 9 blue vertices are the independent set. And that's the maximum independent set. So this is known as clique number. Clique, I have already mentioned, it's a basically subgraph which is complete. That's all. So suppose I have given you a graph. So you can see that this is a subgraph which is complete. Triangle is complete. So this is one clique here. So if I consider this, then this is also a clique, but you can understand that this is not a maximal clique. So the triangle is a clique, but if I consider this, this is not a clique. So that's why not a clique. If I consider the red mark one, then that is not a clique. If I could have this as an edge, then certainly that would be a clique. Here, this is a clique, but not a maximal clique. Which will be the maximal clique? So this is the maximal clique. Here, this is a maximal clique. This is a maximal clique. But clique number is the size of the largest clique or the maximal clique. So size of the largest clique. So here you have a clique of size 3, you have a clique of size 3, here you have a clique of size 4. So the clique number for this graph is basically 4 and so on. And that is the last of for the syllabus, and that is known as Havel-Hakimi algorithm or theorem. It says that suppose you are given with a finite set of non-negative integers. The question is, can you find a simple graph such that its degree sequence is exactly the least. For example, suppose I am giving you, in my first class I started with this kind of problem. Suppose I given you a set, say 1 2 3. So this is a finite sequence of non-negative integers. Now the question is, can you find some graph whose degree sequence is like this? So I want simple graph whose degree sequence is like this. Can you find some graph whose degree sequence is like this? Can anybody be able to tell me whether you can find such graph whose degree sequence means I have three vertices such that the degree of this vertex will be 1, the degree of other vertex will be 2, the degree of other vertex will be 3. I need some graph which is simple in nature, but I should have this property. So if I have 1 degree vertex, then I can have the degree of this vertex is 2. That is also done. So I need to have, might be I should draw like this. So the degree of 1 is already done. So this is already done. The degree of this vertex is 2. That is also done. But I need this degree to be 3. How to make the degree to be 3? That too for a simple graph. If I draw like this, then its degree will be 3. But I do not have any loop or any parallel edge. I also cannot have like this because I am actually considering simple graph. So in a simple graph, you cannot have parallel edges or a loop. So can you really draw such graph? And this algorithm states you that whatever be the sequence of finite sequence of non-negative integers you should give, then suddenly this algorithm will able to tell you whether you will able to construct such a graph, simple graph with that degree sequence or not. So that's the known as Havel-Hakimi algorithm. You may Google it and you will get this. So in our syllabus, we only have the statement of Havel-Hakimi algorithm or theorem. So if anybody is interested, he or she are welcome to have a look at Google, and it's not very difficult to understand about this algorithm. So that's all about whole the topic, all the syllabus for graph theory. So if you have any question or comments, you can ask me.